All right, AM transmitter using GNU radio. This is what I propose what we're going to do. We're going to transmit two amplitude modulated signals at the same time. We'll have one AM signal at a carrier offset of -5 kilohertz right here in yellow, and we will have another amplitude modulated signal with a +5 kilohertz offset as we show here in green. And we will be transmitting at a frequency center of 151 megahertz with a whopping 0 dBm of transmit power. Now, for those of you that don't know, 0 dBm is basically 1 milliwatt. So, a quick review. A dBm is a log in milliwatt. So the equation is dBm equals 10 times log 10 of milliwatt. So if you take 10 times the log 10 of 1 milliwatt, you will get 0 because it's referenced to a milliwatt. So 1 watt is 30 dBm. It's a very simple equation. If you're not comfortable with logs, no problem. There's plenty of online calculators for you where you simply just put in the dBm and the calculator tells you the milliwatts, the watts, and everything else. The one thing I will say is that dBm is on an exponent scale, not a linear scale. So little changes in dB are significant changes in linear, right? Now someone might ask, why do we use dBm? Why do we use dB units? Why don't we just use milliwatt? And it really is a great question. But when you work in the world of receivers, you have to ask yourself, is it easier to say the sensitivity of a receiver is -120 dBm? 120, -120. I can work with that. That's a pretty simple number to remember. But if you were to say the same thing in watts or milliwatts, you would then have to tell someone this receiver sensitivity is 0.0000000000000000000000001 watt. I don't know about you, but I'd rather have someone tell me -120 dBm than instead of someone telling me it's 0.00000000012 watts. How many zeros was that? Exactly. That is the reason why we use dBm, and it's easier to work in dBm. It's simpler to do adding and subtracting than multiplying and dividing. And when you convert everything into dB units, when you go through an RF chain, you simply are then adding and subtracting the dBs. Okay? If I have an amplifier that has 30 dB of gain, and assuming it can go out up to a watt of output power, if I put in 0 dBm, I simply take 0 dBm and say plus 30 and say, oh, the output power will be 30 dBm. So working in dBs is simply adding and subtracting. And if you can add and subtract, you too can be an RF engineer. It's a dirty little secret. Most RF engineers don't want you to know that. They want to keep it all smoke screen and mirrors and say it's very complicated, blah, 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 blah. But the reality is, if you can add and subtract, you too can be an RF engineer. All right, off my soapbox. So let's get into the GNU radio block diagram of how I'm implementing this AM transmitter. Now I know it looks very busy, but it's basically two streams here happening at once. So let's just focus on the first stream. We're reading in a audio wave file here. That's what the wave file source is. We're going to do some bandpass filtering on it to basically only allow 50 hertz to 5K. Okay, so that's just an audio filter, simple as that. And now we need to multiply it by some modulation constant. That's what this fast multiply is. So I'm going to give it 120% or multiply it by 1.2. All right. Now we need to add the carrier to do AM. And that's what this add constant is. It adds 1 essentially to this stream. So all the orange indicates float, basically indicates real values. We now need to convert this real value stream into a complex stream. And that's what this float to complex is doing. So all of this data is essentially in the I, right? There is no imaginary or Q, so that's why we just say 0, just to keep GNU Radio happy. All right, now we have this complex multiply. So we basically have to take this AM stream here and multiply it by our negative 5 kilohertz phaser. And that's what this guy here is doing. So now this stream is now going to be centered at negative 5 kilohertz. And this part down here is basically the same thing with a different audio file. And we're basically multiplying it by the positive 5 kilohertz. We add the two streams together. We want to effectively get the final rate to the transmitter up to, so the two wave files have a sample rate of 48 kilohertz, right? But we want to send the stream to the transmitter at a sample rate of 192 kilohertz. So that's what this rational resampler does. It's essentially increasing the sample rate by 4. So now the sample rate going to the transmitter is going to be 192 kilohertz. Now, the transmitter values have to be in the range, the samples essentially have to be in the range of 1 to -1. So when you do all this multiplying and adding, you're gonna create your stream, and if you simply plot it, you're gonna see that the max and min go way greater, not way greater, but they go greater than 1 and less than -1. So that's what this multiply by 0.3 down here is. All right, so if you do not have a GNU Radio transmitter hardware, you can still do all this in the program and simply just send it to this time sync thing here, and you'll see the effective complex signal, right? So you don't need any hardware other than your computer to run this GNU Radio companion. So I just want to show you that, if those I'm not going to do that, I don't have this B200 thingy. I'm just showing you can build this flow diagram and use just the PC, and it really is a great way to understand radio signal processing without needing any hardware. Obviously, to me, that's a bit boring, so I do have the hardware. So this is what I sent it to. This is the USRP sync. So a sink is a place where you send data. Think of it like dumping water down a sink, right? This is where we send streams of data. And a source is something where we're bringing data into GNU Radio. So source, we bring data into GNU Radio. A sink is GNU Radio sending data to a device, all right? So here you can see we're telling this hardware sample rate 192 kilohertz. We're telling it a carrier frequency of 151 megahertz. I put the gain up to 50. That seemed to be pretty strong. It was around 0 dBm. So, obviously it's not going to have much juice. You're going to need some power amplifier, but for me, just to test it within my property here, 0 dBm was plenty of power. And I set the bandwidth to 180 kilohertz. All right, enough of the blabbing. It's time to show me the money. The proof is in the pudding. So let's do a demo of this thing working.
You are listening to amplitude modulation with a carrier offset of -5 kilohertz. Thank you for listening and have a great day. To know the cutting edge, continue watching the GMR 140 YouTube videos. You are listening to amplitude modulation with a carrier offset of +5 kilohertz. Thank you for listening, have a great day, and continue to watch the GMR 140 YouTube videos, constantly exploring the world of radio electronics and radio mathematics. If you would like to know the cutting edge, continue watching the GMR 140 YouTube videos.